Hello, I trust all is well with you. So we're going to do lecture E4. Um, I think this is one of my favorite lectures so far, and you'll see why. It contains some pretty nice results for graduate level econometrics. So what we have ahead of us is something called mean square error, BLP best linear predictor, and CEF conditional expectation functions. And in this lecture, of all the lectures, I mean, I say this all the time, but this one, intuition is paramount. So, one of the ways I'm going to try and motivate this topic is as follows. You remember your good old undergraduate simple OLS model. Somebody wrote down an econ model, and then you kind of had the story that in real life the model doesn't fit, it's not perfect, there are unexplained or omitted factors. So there's always an error between the actual value of y in real life and what the model says it should be, which is y hat. And to estimate the parameters of your economic model, you would set up an econometric model, OLS. You would estimate the beta 0, beta 1s by OLS means ordinary least squares. So you minimize square of errors. And then you would show that the slope coefficient was the covariance divided variance. And the intercept would then be the mean minus beta 1 times the mean of x. This is your standard simple OLS model. One of the things which is kind of sad about undergraduate econometrics is not only are they taught by boring econ profs, because all econ profs are boring, so by definition we can't be spectacular, teachers or lecturers. But this is one of those things where I feel that the econ profession can in fact do better because most people, when they are first introduced to regressions, are told a story that looks something like this. There's a true model out there. So, for example, I could claim that my company's product has a downward sloping demand curve. And then I wave my hands and I BS and say, well, in real life, for example, this should say if you're selling this much quantity, sorry, I take it back. You should, if you were charging this price, you should sell that much ice cream, for example. And the proverbial econometric prophet says something like, well, on this day, if I set this price, I should sell this much ice cream, but perhaps that day was a cold day. So the actual sales of ice cream were lower than what I should be. Perhaps on a different day, if I had set this price, I should sell that many ice creams, but it was a particularly hot day. Or perhaps some sports team won a game, and so people felt happy and they ate ice cream because that's what you do when you are happy. You eat ice cream, right? And so sales of ice cream were higher than what the model says. So some days it's higher, some days lower, and it's kind of spread around the true econ model. And then your only job now, of course, is to then fit a line, the best fitting line that minimizes square errors. That story was some story that kids are given. Another story that you might have heard as an undergrad was something like, well, if you look at this scatter plot long enough, it helps to have several tequila shots. Then you start to notice that it looks leaderish. Like if you had to describe a line, like you'd be wacko to claim that this model line describes that data. You probably say, if I look at the scale long enough, it looks leaderish, so I could probably, model these observations by a linear model, hence your linear regression. So story number one is about I know a priori that I have a linear model, and then there are things that are random, that cause actual observations to be different from what they should be. Second thing story could be I look at reality. I think I can see that its underlying model should be linearish, and I estimate the equation of that linear model. Now, this is one of those things where, like your ex girlfriend, boyfriend, ex bae, you should forget about them. In the same way, you should forget about these stories of regressions. Neither of them are acceptable for graduate school. Neither of them is the right way of thinking about econometric models. The right way of thinking about econometric models is as follows. As an econometrician, now that you are in grad school, you can call yourself an econometrician. Please don't introduce yourself as an econometrician at parties. No one's going to talk to you. But we're not at a party, we're at Echo 1010. So you can call yourself an econometrician. You understand that when you talk about y's and x's in a quote unquote regression model, what you really are trying to say is that y and x have a joint distribution. You've done billions of joint distributions by now, so everyone should understand what I mean by this. That there are two random variables x and y that have a joint distribution PDF f of xy. What you want to do is you want to someone comes along, gives you a value of x. You know, let's pretend that for 2 seconds you know the density, the joint density. If you knew the density and you knew the value of x, your job then is to predict the value of y hat being the y corresponding to the x. Because remember, x and y are jointly distributed. So if I give you a value of x and you know the PDF, your task as an econometrician is to predict the value of y. And here's where it really upsets me when people in, for example, organizational behavior, sociology, psychology, Marxism, so forth. They accuse economists of being poor forecasters. Oh well, the forecast is off. Well, of course it's off. It's the whole point of forecasting. We're not idiots. We understand that any forecast, by definition, is going to be off in the sense that it's going to have a bias. And by the way, here's one question. If I actually was going for a, let's say, BCG interview, you of course know what BCG is, bad consulting group. One question that could be asked is a forecaster consistently uh, misses the forecast is always off. There's always biased. They're always 5 units off. So, but if I'm always 5 units off, then knowing that I have a bias is a good thing because if I'm always off by 5 units, all I have to do is make a forecast and adjust by 5 units. So bias is not a bad thing in forecasting. You have to accept it, just like many things in life. Uh, Maybe you're not the fastest person on this planet. Accept it. In the same way, you have to accept the fact that no forecast is perfect. There's always going to be an error between the actual value of y and y hat. What you want to do is, knowing that there's going to be an error, utilize that to your advantage and try to come as close as possible to y. But in what sense? In one of the following sense. Rhetorical question number one. If you give me an x from a known density of x and y, how do I go about forecasting the value of y? And if I'm asked to do so by using a function, an equation of x, which is designed to minimize the squared errors, then what would that function be? So once again, give me an x, I know the density, I want to use a function of x, some other equation of x, to forecast the value of y, but my criterion for quote unquote minimizing errors is to minimize square errors. For those of you who are sophisticated econometricians, you should remember that there are many ways to define good forecasting. One way that we're doing is, of course, to minimize the square errors. Somebody else can come around and minimize the absolute errors. Someone can minimize the percentage errors, etc., etc., etc. But if your job criterion is to minimize square errors, the answer is you should use something called the conditional expectation function, which in fact you've seen before. It simply says the best way to forecast the value of y given an x is to use the equation for the expected value of y given x. I've talked about this in the previous lecture, and I showed that how this was a function of x. Well, can and probably is most often a function of x. As opposed to a slightly different question, once again, give me value of x. I know the density. Again, I want to estimate y. And again, I want to do so by minimizing squares. But this time, the key difference is instead of using some function of x, I want to use a linear function of x, something that has an intercept plus a slope times x. So if I'm using any function of x, I would use the conditional expectation function. But if I'm using a linear function of x, then what I should be using is something called the best linear predictor, BLP. And you start to notice that the BLP looks suspiciously like the OLS. I'm insisting that you forecast by a linear model. I'm actually going to prove with you that this coefficient is in fact going to be exactly what you get by running an OLS. So a little bit of thought should say, wait a second, I've done enough exercises by now to understand that this creature may or may not be linear. So the best ideal, if you were truly, if luck was on your side, the best way to do any forecasting is to always use the conditional expectation function. Expectation of y given x, which may be linear, which may not be linear. You don't know. And if you don't know this, perhaps the next best thing you could do is to use a linear function, which is the best linear predictor. And of course, in applied econometrics, graduate school, your fantasy, the best holy grail, is to work with x and y's where it turns out that the conditional expectation function, which is what you should be using, in fact turns out to be a linear function. So the two things are coincidental, right? So if you run, so another way to understand this is this: when you run a linear regression, but the underlying conditional expectation function is non-linear, then OLS is horribly off. But if you run OLS on something where behind the scenes the conditional expectation function is in fact linear, boom, you have hit the holy grail, right? This is the best thing you can actually hope for. Well, let's see when this happens. So I'll do this by three cases, progressively harder and harder. Your job is to forecast y hat. In case number one, somebody observes, and you should pay attention to what information I'm giving you and what I'm asking you to do. Some analyst has observed a particular value of y from a PDF of y. This could be normal, this could be any of the PDFs that you've seen so far. She doesn't tell you what she has observed. Your job is to guess that value of y or forecast the value of y. And in case number one, we restrict your forecasting rules. She has observed a value of y. You must come up with a forecast which must be a number. It cannot be a function of y. It cannot be a function of y squared. It just must be a number. What's the best number? If your criterion is to choose that number to minimize the mean squared errors. Because you're working probability models, you won't say you want to minimize the expected value of the error squared, which is exactly what you see over here. Now, something different. See how the information has changed? I'm going from a marginal PDF to a joint PDF. Some observer, an analyst, has picked a particular value of x and y. So there are x and y's here. She picks one pair, x and y. She doesn't tell you the value of y, but she does tell you the value of x. So she has observed x and y. She sends you a WhatsApp message here, what's up, here is the value of x. Given that value of x, your job is to forecast the value of y. And you're asked to do so by using some function of x, yx, because you know that y and x are jointly distributed. She has given you an x, so why not construct some function of x, which you don't know yet right now, to forecast the value of y. So the first time in this course, you're doing something that you've probably never done in your life before. Here, your standard calculus. Choose a number to minimize something. But now you are not choosing a number, you're actually choosing a function. So what is that function that minimizes this creature, right? And that's not something you can answer by straightforward calculus anymore, because you're guessing a function, no longer solving for a value of x. You're trying to ask what the function is. Is it x squared, x cubed, square root of x, log x? Who knows? In the third case, we once again come back to somebody picking a value of x and y from a known PDF of x and y. Once again, she tells you x, and your job now is to use that value of x to forecast y. But instead of using any function of x, quote unquote, right, you now are going to use a linear function of x. So you're now narrowing your choices. Instead of any function of x, big giant thingy, you're looking at a subclass, smaller set, which is only linear functions of x. And the question now is, if that's the case, what would beta 0 and beta 1 be? So now, once again, you're back to normal calculus. You're going to choose numbers. So let's start. In case number one, let's go back in. The idea was you know the marginal PDF of y. Somebody observes, picks a value y from that distribution, and you need to come up with a number that's the best guess of what that value y is. Let's do it. If your criterion is minimize square errors, mean square error criterion, you want to choose baby c to minimize this expression. You should now have enough practice. You should know how to go from here to here. I mean, you can, for example, you can square this term already and remind yourself the expectations are actually a linear operator that pass through. So in 5 seconds, you can take the derivative. That's the first order condition. And over there, voila, you're done. So you can show that, aha, if you have a PDF of y and you're asked to forecast some value of y in real life, the best thing you can do is to pick the center of the distribution or the expected value of y. And now I hope you have a deeper understanding of why we use the words expected value when we compute this expression. Literally, it's the best number to of what you expect to happen in real life. Example. You remember the joint PDF of x and y a long time ago? You remember how we pulled out just the PDF of x, just the PDF of y. If somebody says, give me forecast, my friend has picked a value of x from this distribution, and you need to come up with one number that's the best forecast in the sense of minimizing mean square error, the best thing you can do is to name the center of the distribution or the expected value. So you would say, listen, the best guess of the value of x in real life is 3/4. In the same way, if someone says somebody's observed a value of y from this distribution, and you're asked to make a forecast what that value is, and if the criteria is to minimize square errors, the best choice of that number is the center of the distribution, or in this case, the expected value of y, 3/8. Beautiful. Now we go to the more complicated question. Now you have a joint PDF of x and y, like your good friend that you've been working with thousands of years. Let's do an example. Let's say my friend, she goes out and she picks this particular x1 and y1. Okay, so she's picked the red dot. So I know that, and so she has picked this particular red dot. She sends us a message. She tells us what the value of x is. So this particular instance, she tells us what the value of x is. Let's say x1. It's day one. So I know that if she's telling us the value of that pair of x and y was x1, then we know that the y's must be somewhere here, somewhere on this line. Where else would they be? Right? They can't be here, no, up there. And what we then have to do is to pick the diamond, a forecast value. And the forecast and the actual value obviously have an error. So we want to choose the diamond in such a way that we minimize the expected square errors. On a different day, she could pick this, she could observe this purple dot. And she could have sent us a message saying, listen, I see the value x2. On the second day, if she tells you that she has observed x2, on the second day, you know that the value y must be somewhere on this purple line. And once again, you have to come up with a forecast by picking a diamond. And the criterion is to make these expected square errors as small as possible between the diamond and the dot. Now, we want now, remember, on day one, here's your forecast of diamond. On day two, here's your forecast of diamonds. If I now were to do this again and again, day 3, day 4, day 5, I would have a bunch of diamonds. And maybe if I connect the diamonds by a line or a curve, it may look something like this. So once again, the blue line is just for intuition. It shows you is the locus that connects all those diamonds. What do you mean by diamonds? All those forecasts that are designed to guess the value of y given a value of x. And I know. So we're not going to make you do that derivation right here. If you were doing a PhD econometrics, you'd be asked to do this. So the derivation of this function is way beyond the course. The question is, what is that function? What's that equation of x that can be used to feed in the value of x and predict the value of y? And the answer, my friends, is one of the most important results in econometrics. If you're going to use some function of x to predict the value of y, your best choice is to use the expected value of y given x, which is also known as the conditional expectation function. Now, before going to the next slide, you should really think back to the previous lecture and say, did that even make sense? And you should, before I show the next slide, remind yourself what this is. The expected value of y given x is the center of a certain distribution. Which one? The density of y given x. So in the previous slide, you said, give me any density and the best forecast in the center of the density, the expected value. So if you're now working, if I asked to give you a conditional density, and again I asked you to forecast the value y given x, your best thing that you can do is to use the center of that distribution. So the center of the conditional distribution is of course the expected value of y given x. So it's not rocket science. You could have used intuition. But of course in PhD econometrics you have to use math to produce the result. Just to drive this point home one more time, once again you have your distribution of x and y. I purposely show you here the distribution of x, purposely show you here the distribution of y. And now once again, remember that to illustrate what's going on, if somebody says, listen, pick a value from the distribution of y, what's the best forecast? The best forecast is simply the center of that distribution, expected value y. As opposed to a completely different question which says x and y jointly distributed. Somebody tells you the value of x, that's x1. You know the value of y should be somewhere on that line. Which value, what's your best forecast? Well, as you've shown you in the previous lectures, for any value of x, there's a distribution of y given x. So this red curve is the conditional distribution of y given x1. And that has a center of the distribution, which is expected value y given x1. That's going to be a forecast of y1. On the second day, she tells you x2. Once she tells you x2, the value y2 has to be somewhere on this dashed line. What value should I pick? Again, there's intuitively a distribution of y given the value of x2. It has a center like any distribution. And that center, of course, is the expected value y given x2. And that should be your forecast of y2. And if I were to look at this picture, how gorgeous is math and stats. Actually, if we look at this picture and literally look at this picture, it shouldn't surprise you that if I were to pick this value of x, once again, intuitively there'll be some conditional distribution, which will again have a center. But it's not hard to see by this picture, right, that in this particular example, if I were to connect those things, they will probably end up being linear. I don't know yet. All I know is the right way of finding out what the equation is to literally compute the expected value of y given x. And I'll be very lucky if maybe it's linear because you can see by this example it kind of probably should be linearish. Let's check it. As I've shown you in the previous lecture, as you have shown yourself, the expected value of y given x is found as follows. You take the value of y, you then, since you're doing conditional expectations, you multiply with the conditional distribution of y given x. Since you're talking y, you integrate y, and for God's sakes, on the exams, tests in life, advanced mathematics, all that stuff, you got to be careful of the ranges. Once you give me a value of x, the value y has to go somewhere between this range right here. So it has to be the value of y should be between 0 and all the way up here, which of course you know is the value of x. So that's why you see the range of integration from 0 to x. Yo, you got to do this. You actually got to work it out. Take the y, do the whole thinky winky winky, and you get a gorgeous result. It was only linear because of the specific example I've chosen, but it need not be linear, as you're about to show in a different example. But the real rule that you want to remember, take away from this is, if anyone asks you ever in life to forecast a value of y from a value of x, the best thing you should do, the only thing you should do is to sit down and compute the expected value of y given x equation, which may or may not be linear. Once you find that equation, feed in the value of x. So this particular example, I would feed in x1, and given the value of x1, I would get a forecast of the value of y1. And that's the best thing that you can do to minimize the square errors. And yes, we did expect this to be linear because of the way this particular example was designed. So let's let me reinforce this concept one more time. Take a look at this next example. You've seen this one before too. See, I've saw all coming together now. So it's a joint distribution of x and y. Once again, your good friend goes out and observes a particular value of x and y. She tells you the value of x on day one. Given what she told you, the value of y, what she saw, has to be somewhere here. Where exactly? Find the conditional distribution. So this red line is the conditional distribution of the distribution of y conditional on x1. The center of that distribution, of course, is this thing right here. But if she picks a second day and she again gives the value of x, again the value y must again be on this line somewhere. And because notice how this is square support. I talked about this in God knows what lecture. Because it's square support, you shouldn't be surprised if the conditional depth, the distribution, has a center that's exactly equal to this. So if you're having a hard time understanding this, imagine this is a loaf of bread. If I slice the loaf of bread here, the center of that slice will be exactly located at the center of this slice. So even though the height, this bread is really weird. At x0, y0, the bread has zero height. But as I move in this direction, the bread is getting higher and higher. See? Because it's proportional to x squared and y. And you can see this on this three-dimensional picture. But the tricky part is that but for any one slice of bread, and really imagination really does a good job here. Once I slice the bread this way, and I look at the conditional distribution, it has some center. But if I slice the bread at a different place, and I again to the center, it'll be exactly on the same horizontal line. And because the bread is getting higher and higher and higher, as right for higher values of x and y, that line need not be at 0.5. The only way to find out what the line is to compute h of x. Once again, what's h of x? On Friday, you will be asked this question 101%. All you have to remember is the best function of x that can be used to predict the value y is the expected value y given x, which in this case is as follows. Again, y multiplied by the conditional density y given x, integrate over y. But now, what's the range of integration? That's the only thing that throws people off in exams. And again, by pictures, once you give me a value of x, notice that y has to be somewhere between 0 and 1. That's why you have 0 and 1. So I will leave this to you to work out the numbers, and once you do so, the answer is always 2/3. So it doesn't matter what value x she gives you. In this particular example, like a broken record, you keep saying 2/3, 2/3, 2/3 is the best forecast for any value of x. And again, just to drive the point home, again, just to make sure that we can get this right, now I give you an even more devious thing, which looked a little bit like what you saw earlier, right? So I did this on purpose because it looks like this example, right? See that the support is triangular. The support is triangular-ish, but the difference was over here, the height of this 3D surface was proportional to x. So as you moved in this direction, this surface would get higher and higher. But if you moved in this direction, it would stay flat. As opposed to this one, where if you move in the x direction, it doesn't change height. But because it's proportional to y, as you move in this direction, it does change height. So one suspects that the conditional distributions of y given x, when you correct the centers, may not be a straight line. This was, in fact, the test 2 question last year. You have the solutions, you have the question, you have Thursday evening. Since you're at, since you're still in your undergraduate mode, I suspect that the exam is at 10 o'clock in the morning on Friday. The way that at least it works at U of T undergrad, people start studying at 9:58 a.m. Or they could say it's an open book and wing it. Well, don't wing it, right? Wing it is for leave it to the wings. Okay, so all you have to do, ladies and gentlemen, is to compute the expected value of y given x. And if you do so, you'll get this nasty equation that shows you that, in fact, the conditional expectation function can, in fact, be nonlinear. So once again, it's a very rare case, not rare, I should say, but it's very unusual that the conditional expectation function just so happens to be linear in this example. It just so happens that the conditional expectation function happens to be linear, as in this example. But more often than not, when you work with real life thingies, if you're working with conditional expectation functions, they tend to be non-linear, as an example right here. So this now means that in practice, if you start to get a headache, because this is not easy to compute, if computing this creature is really hard to do, maybe the next best thing you could do is say, you know what, I don't have too much on my plate to work out the actual conditional expectation function. It's too non-linearish for me to work it out. Maybe I can approximate it by a linear function of x. And that's exactly what you do in case 3. Case 3 once again says the same story. Give me a value of x, forecast the value of y, knowing the density of x and y. And what you now want to do is you restrict yourself to linear functions of x. Again, the intuition being that maybe you don't want to compute this expression. And what you want to do instead is to compute, rather than computing this expression, you want to compute the linear, best linear predictor, which means for the time being in this slide, you're forcing yourself, instead of working with any function of x, which is a massive class of functions, you're working with a smaller subset, the set of linear functions. Okay? So in that case, what would beta 0, beta 1 be? And this, when I first saw this in grad school, I have to admit, I went out and had a few drinks for like a week. Because not only, we're about to fit a straight line that's going to be used to take a value of x and predict values of y. Wouldn't it be gorgeous if you got a straight line which just so happened to have the same intercept as an OLS intercept, and which happened to have the same slope as it is as an OLS slope? Behold the magic of statistics and mathematics. We want to choose intercept and slope to minimize mean squared errors. So now here's y. You're trying to predict this by a linear function of x. You got to work out the math, guys. Open the thing inside, have a few shots, do it. And you will prove that the slope coefficient is this, excuse me, and then the intercept is this. And this is known in statistics and probability as the best linear predictor, because what you've done is, instead of wanting to work with the actual conditional expectation function, which may or may not be linear, you are forcing yourself to work with linear predictors only, and these are the coefficients. And this is where you should rejoice and sing happy songs, because it turns out that the intercept and the slope are identical to the ones from OLS. Isn't that amazing? There was no guarantee that they should be, right? Because OLS could give you this line and BLP could have given you this line, but what the math shows you, those two lines are in fact exactly the same. Gorgeous. Therefore, coming back to this example right here, I already know in this example, because I did it some time back, that the conditional expectation function was x over 2. I knew it was linear to begin with. And now I want to see what will actually happen if I do the BLP. Well, surprise, 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 since you're trying to approximate the CEF with a BLP, and since in this example the CEF happens to be linear, then it shouldn't surprise you that the BLP and the CEF in this example will be exactly the same. So you need some ingredients, because for the BLP, you need to compute this expression. So you need to know what? You need to know the expectation of x and y, x times y, expectation of x, expectation of y, expectation of x squared, and of course, expectation of x. Those are given to you all up here, right? And then to compute beta 0, you need to know expectation of y, which you already have upstairs, expectation of x you already have upstairs. I urge you to do this. So once you have all these things, do this thing, and the equation comes out to be, beta 0 turns out to be equal to, right here, 0. Beta 1 comes out to be equal to 1 half, and therefore the equation is going to be equal to x divided by 2, which is the exact same equation you got with the conditional expectation function. You had to, because CF was in fact linear. So rejoice, because the best thing that if you can do as an econometrician, if you're working with models where you're using x's to predict the y's, is to dream, fantasize, hope, pray for a conditional distribution where the CEF is linear. Because in that case, when you run regressions, the two things are going to be exactly the same. So your regression model would be a perfect fit, no pun intended. So this begs the question, fantasies are fantasies, right? You know that the conditional expected function, as this example, could be nonlinear. So you're like saying, yo, wait a second, wait a second. Would it be nice if I always worked with x and y's where the conditional expectation function was linear? So you should be saying to yourself, what kind of witchcraft is he about to pull right now? One more time. You're an econometrician. You're in grad school. You're working with a model of x and y, joint density. You know that the expectation of y given x for your model is non-linear. But non-linear things are nasty to work with. Wouldn't it be nice if somehow you could always work with model, any model where the conditional expectation function instead of being non-linear was linear? How can we do this for any joint distribution? Is there some way that you can take this joint distribution and play tricks on this so that in applied work, empirical work, you're always working with conditional expectation functions that are linear, so that BLP and CFs in those models would be the same? Here's how you do it. It's going to take a few steps. The way to do this, well, here's your homework, is as follows. Okay. Are there any PDFs out there in real life which always have a CEF, expected value y given x, which just so happens to be linear? That means they coincide with the BLP. And the answer is yes, if the x's that you're working with and the y's you're working with are jointly distributed by weight normal, we're good. Cool? But then you should come back and say, but Ajaz, that hasn't solved the problem yet. Because what you've done is you promised me a trick where I could take any density, such as this one, and play tricks on it so that if I'm doing applied empirical work, I would only be working with functions CEFs that are linear. You haven't done that because you've told me rather than working with this particular joint density, you're telling me to work with a joint density with the x and y's of a joint distribution by weight normals. Okay, you're right. But the trick is, once I establish this result, then what's going to happen is I can take any joint density, such as the one I showed you right now, and do some magic tricks on it so that what you're left with in terms of data are x's and y's which happen to be bi-weight normal. So once again, we're going to see a trick where you can take any joint density, pull a trick, and with the quote unquote x's and quote unquote y's will be guaranteed bi-weight normal. In which case, we can then securely work the fact that the CEF is in fact linear. Let's first show this result. Excuse me. So, some probability models. We begin with the normal model or the Gaussian model. This fella right here, uh, pretty cool. I don't know if you have a chance to look at this note. Do you guys notice something? No, you don't? Come on. Okay, what about this thing right here? Dun, dun, dun. Normal distribution. So that dude, Gauss, quote unquote, came up or discovered this thing. Hence why it's in the Deutsche mark. Now, I'm going to do the following. I'm going to show you, and I think this is useful because I'm going to show you how to think about normal distributions with one variable, and then I'll then show you how to think about normal distributions with two variables. And you remember that in one variable is something called standard normals and simply normals. In the same way, in bivariate, there'll be standard bivariate normals and bivariate normals. What in God's names are those? Let's start with a standard normal. I now claim that y is a standard normal random variable. What that means in words is if you tell me that y is standard normal, here's the equation of the density. You remind yourself that in this case y goes to minus or plus infinity. Because it's standard normal, you remember from your undergraduate days that it must have mean 0, expected value 0, and the variance must be equal to 1. And of course, you remember this fantastic notation, which everyone understands is the universal notation for standard normal. Y has a normal distribution with mean 0, variance 1. Now we have x, not y, which is simply normal, ain't standard normal. If anyone writes down non-standard on the test, I'll break their knees or pens. What does this mean to say x is normal? The way you do this, and I think you should do this at some point in your life. Well, actually, you should do this because I ask you to do it in a few seconds. Start with a standard normal. And then what you do is you come up with a brand new definition. You invent a brand new random variable x that's equal to a number called mu plus a number called sigma times y, which you know is a standard normal. Agree? You should be able to show from this equation, you should and must derive the expectation of x and show that's equal to that number mu. You should be able to use the rules of variance and expectations from previous lectures and find the variance of x and show that's equal to sigma squared. So when x is equal to mu plus sigma y, where y is originally a standard normal PDF, you come up with what's known as a normal PDF, whose equation is this. X minus mu divided by sigma is a standard normal distribution, and x itself is normal distribution with mean mu and variance sigma squared. And here are some examples that I've shown over here. Right? And then notice that because of this relationship, you can always go back and forth between a normal and standard normal, as I've shown you over here, which you should do study on your own. Agree? So we have seen one variable standard normal, one variable normal. And now you know where normals come from originally. In the same way, we'll do the bivariate cases. Uh, in passing, I should remind you of the 68, 95, 99.97 rule, which you can read on your own at some point. The appendix, by the way, gives you Excel commands for finding these things out. Now let's do the bivariate one. Pay attention to the title slide. Now you have two variables, right? Because it's bivariate, bi, two. Z1, Z2 have a standard bivariate normal. So it's the analog, the cousin of the standard normal. What does that mean in plain English? To find something that's standard bivariate normal, you begin with two standard normals to begin with. Y1 is standard normal, Y2 is standard normal. And then you define Z1, Z2 as follows. Z1 is equal to Y1, and Z2 is equal to this weird equation right here. I hope you appreciate from previous lectures. Remember how we said, given a PDF of x1, x2, you can find the PDF of a function of x1, x2, and I reminded you that of maybe you could be given one function of y in terms of x1, x2s, but to find the PDF of y1, you would have to invent a new y. So that's exactly what you see here. So z1 is exactly equal to y1. So you know this has a normal distribution with mean 0, variance 1. Agreed? Oops, 1. But Z2 is this creature right here. Please, por favor, with the cherry on top, I need you to use rules of expectations and variances to show that the expectation of Z1 is 0, of course, because it's the same thing as Y1. Show that the variance of Z1 is 1, because it has to be. Show that the expectation of Z2 is also 0. And I want you to find out the variance of Z2 on your own. And then it turns out that once you define Z1, Z2 this way, Z1, Z2 have this distribution. And what's beautiful about this distribution is that even though it's a distribution of two random variables Z1, Z2, it is in fact only depends on one parameter called rho. So what does that mean in plain English? Notice how the normal distribution, if you want to graph this entire normal distribution, somebody has to give you two parameters. They would have to give you the mean and they would have to give the variance. But in order for you to graph the standard bivariate normal, someone only has to give you one number called rho. And rho was the number defined here. And I'm telling the rho is the number that takes a value between 0 and 1. So you start to wonder, wait a second, a number between 0 and 1. He's calling it rho, and it's between 0 and 1. Maybe it's got something to do with correlations. You are correct, but correlation of what? Which I'll explain in a few seconds. So, to draw Z1, Z2, you just need one number rho. Examples. Here is Z1, Z2, where rho is 0, 0. I did this on purpose. Take a look at this. Right, you can, if you look at the mountain this way, you can clearly see it's normalish. If you look at the mountain from the Y perspective, it's also normalish, right? The dome is symmetrical, and you can see the contour plots are perfectly symmetrical. Now I make rho negative. I know it's not right to say this because I haven't shown you that rho is correlation, but let's imagine it was a quote-unquote correlation. Being negative, the relationship between Y and X should be on a negative slope, so it gives you like this. And now this is where rho positive. Interpret this temporarily as a correlation, which is not quite right. You notice that the Y and X's have a quote-unquote positive relationship. So here are three examples. Standard bivariate normal, which you only need one parameter rho to graph. And these are the cousins of the standard normal distributions in one variable. So we've done this, we've done this, we've done this. Now we come to the analog or the cousin of normal distributions, but now with two variables. Once again, we start as follows. You begin with Z1, Z2 with standard bivariate normal. You're actually doing the same steps as you did before. So go back to right here. How did I move from standard normal to normal? I define x number plus number times y. In the same way, look at what's happening here. Right, so I start with Z1, Z2, that's standard bivariate normal. Excuse me. I define an x, which is like this. I define a y, which is like this. And by the way, boys and girls, it's 2 seconds of work to show these things right here. And you notice that if I define x and y this way, x is a normal distribution, y is a normal distribution with those means and variances which you defined over here. Again, you now have enough knowledge to compute the value of y, expected value of y and x. Now, of course, you know the answers because I know the expected value of x should be mu x. I know that the variance of x should be sigma squared x. But how can you show them directly from these expressions using the rules of adding variances and expectations? Show them. And it turns out, if you start with a standard bivariate normal distribution, define x and y as this way, then x and y have what's known as a bivariate normal distribution. But this bivariate normal distribution now, to graph it, requires 5 numbers. You need to know mu x, which you now know is the mean of the x distribution, which behind the scenes is normal. You need to know mu y, which is the mean of the y distribution, which behind the scenes you know is normal. You need to know sigma squared y x and sigma squared y, which you know behind the scenes correspond to the variance of the x distribution, which you know is distributed normally, and sigma squared y, which is the variance of the normal y distribution, which you also know has a normal distribution behind the scenes. And to top it off, sigma xy, which of course you remember as being the covariance. And now, what was that rho that we showed some time back? Remember, there's a rho behind the scenes. That rho came from where? That rho was defined earlier, and now that we have this slide, that rho turns out to be the correlation between this xy and that y, right? This xy that you see that you define over here. And here's an example that I've drawn over here for you. So, let me summarize a little bit. Okay? To graph the standard normal, you need to know the mean is 0, variance is 1. To graph a normal, you need to know mean and variance. To graph a standard bivariate normal, you need one number, rho. To graph a bivariate normal, you need 5 numbers. 2 means of x and y, 2 variance of x and y, and the covariance of x and y. And here's an example. Why are we making such a big deal of this? Here's why. Prepare for gangster result number 1. Consider somehow, let's now you want more time in econometrician. Okay, let's pretend for 1 second that you are somehow working with a model where you know that X and Y have a joint PDF, exactly as I did assume at the beginning of this lecture. But this time the joint PDF is not your 3x, not the triangle, not the weird things you saw earlier, but it's known to be bivariate normal. If that's the case, one can show, okay, putting this on the test would be too mean. Okay, fine. And let me think about this actually. One can show that density, conditional, the conditional density of, sorry, the density of y conditional on x is a normal distribution. Beautiful. Wow. Amazing. X is normal, y is normal, but the density of y given x is also normal. And you remember the first term is the expectation, second term is the variance. What's this actually? By definition, this must be the expectation of that thing right here. So, boys and girls, you've just shown that if x and y are secretly behind the scenes have a bivariate normal distribution, then the expected value of y given x is guaranteed to be a linear function of x. Wow, 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 we want, right? So the conditional expectation function is in fact linear. Beautiful. So if you ever have a fantasy of working with a x and y's where the conditional expression function was linear, you can always work with x and y's which are bivariate normal distribution. But perhaps maybe you were celebrating too soon. You haven't shown yet that the beta zero and the beta ones are the same beta zero and beta ones as OLS. But that comes next one. In fact, if you were doing and you could do this, you can show that you get the exact same beta zero and the exact same beta one as the BLP slash OLS. So you've proved a really beautiful, gorgeous result. You asked, are there any joint PDFs between X and Y which are useful in real life whose CF is always going to be a straight line? One whose conditional expectation function is in fact the BLP. And the answer is yes, when X and Y are bivariate normal. So, you know, it's reasonably common in real life to find X and Y's which are bivariate normal. Right? We can think about this, right? It's not as simple. Some of you might be saying, okay, that means that if I was to go to graduate econometrics, maybe you're telling yourself that all you should do is you should look for an X that's normal and a Y that's normal, and somehow the two of them together are bivariate normal. That's actually not true. You can't take an X that's normal, you cannot take a Y that's normal, and somehow combine the two and somehow assume they're bivariate normal. They actually have to obey these relationships behind the scenes, and those relationships behind depend on those relationships behind the scenes. But regardless, it is conceivable and quite common to find out X and Y's which have a joint bivariate normal distribution. So you have reason to celebrate. But you're not really satisfied yet because what you really wanted to do was you want to solve the problem of if I was working with nasty, 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 nasty functions, if you've forgotten, like, oh, jeez, okay, this is a bad idea. The heck is it? Like this thing, slide 13. If you're working with this nasty PDF and even nastier non-linear CEF, I promised you a way to somehow get around this and work with CEFs that are going to be straight lines. Here's how you do it. To do it, I must show you the excuse me. I must show you something called the univariate one variable central limit theorem. Then I'll show you the bivariate central limit theorem. And then I can show you how to use the bivariate central limit theorem to convert any quote unquote joint PDF and make it useful for in real life empirical work. I really feel sad for our undergrads because the CLT is so poorly taught and I'm going to do a really shitty job of it. But I hope that I do a slightly better job than what you saw in undergrad. I'm going to read it out and I really want you to think about what this says. Let's read it out first and I'll explain in words what it means. CLT says Consider the sample mean, right? So as a statistician, let's say you have a sample mean where you collect a bunch of Y's, right? You actually collect n Nancy Y's. Each of those Y's are independent, arithmetically distributed, which means they come from a parent distribution. The parent distribution is Fy, which has a known expectation and a known variance. So, for example, Louis Vuitton bags. The sales of Louis Vuitton bags each day could come from a PDF, which may have some mean and some variance. If I chose a number for n could be 7. So what I could do is I could stand outside the Louis Vuitton store on Blue Earth, and I could 7 days in a row. I would count the sales of day one, Y1, Y2, Y3, Y4, Y5, Y6, Y7. And if I took the 7 Ys and divide by 7, I would get a sample mean of sales of Louis Vuitton stores each week. I can be guaranteed that if the n became larger, instead of now taking samples of 7 days, I took sample sizes of 10 days, 11, 100 days, 1000 days. And as the sample size, so all I'm doing is I'm observing now daily sales for higher and higher number of days. As that n goes off to infinity, so maybe an example like this would be useful. So let's say I work with 7 days in a row. Okay, one day this could be the daily sales. Another day this could be the daily sales. Another day this could be the daily sales. Sample mean. Okay, so average sales over 1 week, average sales over another week, average sales over third week, average sales over fourth week, average sales over fifth week, sixth week, seventh week. But what's this thing is telling you is that you start noticing that some observations start to repeat themselves. All of these crosses are sample means. I'm now giving the frequency. And what the central limit theorem says is, as n goes off to infinity, the distribution of the sample means, right, starts to look normal, whose, by definition, whose center of the distribution should be the expectation of the sample mean, and whose variance should be the variance of the sample mean. But by the laws of expectations that you know by now, you can find out the expectation of, maybe I should do it by highlighted. You want to find out the expectation of the sample mean. You know you should take the expectation of sums of y's divided by n's. Passing the expectation through, you can show that the answer is mu. So this expectation of y, what's the expected value of sample mean? That's equal to mu. And what about the variance of the sample means? So this distribution has a variance, right? Right? What's that? From the rules of variances, I urge you to do this. Remember, they're independent. If they're independent, the covariance between any one y is 0 with another y. In other words, the uh, these sales at Louis Vuitton on a Monday are independent sales on a Friday by assumption. That's not really true in real life, but let's wing it right now, right? Because it's a baby course and starts right now. You should use rules of variances to show that you can eventually show that this will be the answer. So in plain English, I keep observing sales of Louis Vuitton bags each day, and I've chosen n to be 7, which means I'm now collecting weekly averages of 7 days Louis Vuitton sales. As I start to do it again and again and again and again, I start to notice that the histogram looks like a normal distribution, which has a center sitting on the true means of the PDF of Y, the daily sales of Louis Vuitton bags, and whose variance is the true variance divided by n. Right? So, as an example, you know that. So I'm actually going to do by simulations. Okay, so let's take this density. You remember this density? I showed this to you earlier. Like f of x, let's say 3x squared. So I'm very sorry. The CLT was stated in terms of y, but of course you can state it in terms of an x because it's just changing notations. Let's imagine a density 3x squared defined between 0 and 1. I already know the expectation is 3/4. We did this in an earlier lecture. You know the variance is 0.0375. We did this earlier. I'm now going to use a computer to simulate I'm going to pick values of x's from here. How do I do this? I talked about this earlier. You know the CDF of this thing. CDF is right there. By definition, the CDF is a number between 0 and 1. It's because it's the probability of observing a random variable that's less than or equal to some value, maybe x. Since the CDF represents a probability, it's a number between 0 and 1. So what I can do is, I tell my machine, dear machine, pick a number between 0 and 1. Let's call that number maybe r. Okay? So the machine picks a number r between 0 and 1, which I know is the same as the CDF, as long as x's take values between 0 and 1. But that's exactly what I'm asking the machine to do. I'm asking the machine to take values between 0 and 1. Okay? But that f of x is equal to x cubed. So this f of x equal to a number between 0 and 1, which the machine picks at random, is equal to x cubed. So therefore, what is x? Have the machine pick a number between 0 and 1, take the cube root, and those will give you the x's that are drawn from this distribution. And then once I pick one x, I can then pick more x's, and I can do interesting things. What I should see is as follows. Once again, here's what the CLT said. CLT said, give me the sample mean from any PDF as long as all the y's are independently drawn. And if you know that the expectation of y's is mu, and you know that the variances are positive, then it doesn't matter what the original PDF was. The original PDF here is this weird thing right here. It doesn't matter what the original PDF is. It can look like anything you want, regardless of the shape of the original PDF. The sample means are going to have a normal distribution that's sitting on the actual mean of the expected value of y, and whose variance is the true variance divided by n. So in the previous example, I'm going to replace the x's with the y's, right? Because to make it compare the slide. So you have a density, that's where y has a density called 3y squared, whose expected value was equal to 0.75. You know that from the previous slide, and whose variance is known to be 0.0375. What the CLT says is, if I were to generate a bunch of y's, right? Let's say ny. So let's say you at any one fell swoop, at any one point, I generate 5 values of y. If I sum those values of y and divide by 5, I would get the average value of y's for those 5 observations, right? Because I've chosen n is equal to 5 at the time being. Okay. And what you're saying is, if I kept computing the sample mean of 5 observations again and again, so I press the computer button, it generates 5 values. I find the sample mean of 5 values. I press the button again, it gives 5 new values and the sample mean of 5 values. And I'm always now computing the sample mean of 5 observations again and again and again and again. If I repeatedly keep finding out the sample mean of 5 things, it should be looking normalish, looks like a bell curve-ish, whose center should be sitting around 0.75, and whose variance should be 0.0375 divided by n, which n of course is equal to 5 over here. Agree? So let me show you how to do this in Excel. So I urge you to download this Excel add-in over here. Let me show you what I'm basically going to do. So what I've done here is, here are your observations. So you can see that if I go down, I have 2 scenarios. In scenario number 1, I generate 5 random numbers from that PDF you see here. And this one here, I generate 100 numbers. This yellow cell here is a sample mean of these 5 numbers. And this yellow cell right there is a sample mean of those 100 numbers. Notice if I press F9, I will keep generating new values. As I generate new values, I keep generating new sample mean of 5 observations and new sample mean of 100 observations. I wonder, this is only one instance of a sample mean of 5 observations. There's only one instance of a sample mean of 100 observations. I wonder if I did this again and again and again and again and again, and somehow kept storing these sample means somewhere, what would the histogram look like? What this add-in allows you to do is just exactly that. So You can read the instructions of the add-in layer on your own. I'll post this file afterwards. But what I'm going to do is I'm going to click on this cell right here. I'm going to go to add-ins. So I've already clicked on B16, and I'm going to tell I'm going to ask the machine to run 1,000 simulations. Click on all ran, and I've also asked the machine to pick the number in C16. This one right here. So basically, what you're telling the machine to do is take the number in B16 and repeat that calculation, store it somewhere 1,000 times. Take the number C16, which is sample mean of 100 observations, store that also 1,000 times. Let us now pray. I hope my computer doesn't crash. Nice. And voila, I have an output. Now the bad thing with this program is it only shows the histogram of the first 100 observations. But you can kind of see the normalist shape. In fact, if we actually go to the actual file, which I'm going to post later on, you will notice that the blue one is the histogram of the sample means of 100 observations at a time. The purple one is the sample mean of the 5 observations at a time. So coming back to our lecture, where is our lecture? This one right here. Let's now see what happens. Yo, this is exactly what I showed you right now. So this yellow cell, first one, is the sample mean of 5 observations, these 5 right here, right? And that yellow cell right there is the sample mean of those 100 observations, right? Every time, so intuitively, the machine now presses the button again and again, F9, and it stores 1,000 observations of the sample means of 5 draws and sample means of 100 draws. And then I'll now make it look pretty for you. The purple thingy is the histogram of 1,000 rounds of the sample means of 5 observations drawn from a PDF of 3y squared. Notice it has a mean. So theoretically, it should have a mean of 0.75. Just with 1,000 observations and with only 5 observations per sample mean, you can see I'm pretty damn close because according to the Monte Carlo simulations, the center of this purple distribution was approximately 0.75178. In theory, the variance should be sigma squared over n, which should be 0.0075. In practice, the purple histogram has a variance that's pretty damn good. So even with n is equal to 5, I'm doing a pretty good job. But when I increase n to 100, the blue line, so now what I'm asking the machine to do is take 100 observations, get the sample mean. And now I collect the sample means 1,000 times. In theory, they should actually have a sample mean of 0.75. In practice, it's 0.75038. Pretty damn close, you would agree. In practice, in theory, the CLU distribution should be sigma squared divided by n, which is 0.0038. In practice, it's 0.0037. Pretty damn good. It's remarkably accurate. And you'll agree with me, it looks normalish, right? And now, of course, if I made n is equal to 200, and it would become even more normal, more normal. Of course, if I had a nice program to do curve smoothing, I could make it better, but I don't have any funds. So now that you're convinced of how the univariate theorem works, let's do some practice. So I'm going to leave this slide as an exercise. You can do it on your own. But now let's get ready for the gorgeous result, the one that will make your life as an empiricist a better one. And which is why it was all worth it to go this pain and suffering and come to U of T. The bivariate version, you want to extend the univariate set limit theorem to two variables now. It says the following. Imagine you took the sample means of y's, and imagine you have sample means of x's, where y's themselves are drawn from the distribution of y's independently, x's are drawn from distribution of x's independently, but you also, where the x's and y's have some bivariate joint distribution. So x and y could have a joint distribution. I draw values of x's only, take the sample means. I take values of y's only, take sample means. And now I know all these values, okay? The expected value of y, expected value of x, variance of y, variance of x. I also know the covariance. Then instead of collecting sample means of 5 observations, if I do 10, 20, 100, the bivariate version says the following. It says if you were looking at the joint distribution, if you were to plot x bar on the x-axis and y bar on the y-axis, the z bar is going to have some distribution. That distribution is going to be, ladies and gentlemen, bivariate normal. And if you remember, bivariate normal has 5 parameters. It would have the true mean of y, true mean of x, the quote-unquote variance of the sample mean of y's, which of course you know from the univariate theorem should be equal to the true variance divided by n. From the univariate CLT, you know it should be the variance of the sample means of x, which of course you know is the true variance of x divided by n. And of course you have covariance divided by n. And there is your beautiful result. So in this example, I know the CF was linear, but I had to do it because you know I didn't have time to make a more sophisticated one. But supposing you want to invoke the CLT over here, right? So you want to take this joint PDF. You have the marginal PDFs of x's, of y's. You have all these results. Let's apply to the CLT. So x and y are jointly distributed. It doesn't matter what distribution they are, right? It's not bivariate normal for sure right now. Agree? You know the mean of x is 0.75, the variance of x is 0.0375, the variance of y is 3/8, the variance of y is 19 over 320. All this is done, by the way, in the previous slide. Okay? And you also know the covariance is 3 over 60. All these items were done in previous lectures. If you were to now collect sample means of y's and x's, they would have a joint bivariate normal distribution. This would be, of course, the mean of, I think oh no, shit, I'm right. Back. The mean of the y's. Sorry. The means of the x's. Here's the variance of y divided by n. Here is the variance of x divided by n. And here's the covariance of x and y divided by n. So even though x and y were not bivariate normal to begin with, the sample means of x and y's are bivariate normal when you account the bivariate normal distribution. So how does it help you do regressions and analysis? Here's the answer. If you have any joint PDF of x and y, and you are not in the mood to compute the expected value of y given x, or you think the expected value of y given x is non-linear, and you don't want to work with non-linear creatures, but rather you want to work with regressions, BLPs, what you could do is your data would not consist of y's. Your data would consist of sample means of y's. So your y's could be incomes. Sorry, your y's could be savings rates. So instead of actually asking for people's savings rates, you could go out and sample 10 people at a time. So your quote unquote y variables that will consist of sample means of 10 people's savings rates. Instead of the x's being incomes of individual people, you could sample 10 people at a time, and your quote unquote x variable would then be the sample means of the sample income of mean incomes of 10 people at a time. And then you could use, then you know that the average savings rates of 10 people sample at a time and the average incomes of 10 people sample at a time have a joint bivariate normal distribution that has those parameters and so forth. But that allows you to do what you wanted to do, which is the following. You wanted a way to be able to give me a value of x and predict a value of y. So the bivariate normal trick says, rather than using a value of x to predict the value of y, why not take the value of the average x and then try to predict the value of an average y? So if you understood this bivariate normal, and if you had understood our previous discussion, then you know the conditional density of the sample means of y's given the sample means of x's must be a normal distribution whose conditional expectation function happens to be linear. Beautiful. So all you have to do is insist that your data not be consist of x's and y's, but rather sample means of x's and sample means of y's. And then you could take a sample, you could take some value for sample mean average income of 10, let's say 10 people or so, and then you can predict the average savings rate according to the condition expectation function, which is guaranteed to be linear, thanks to the bivariate normal distribution. And incidentally, what's beta zero? Well, you can see that the value of beta zero, beta one, in fact, turns out to be, if you actually look at the numbers, this is even getting better and better. The ends and ends cancel off and go to heaven. Wow, so cool, right? And then, of course, nothing in this expression will depend on n. So those OLS coefficients don't really depend on those values of n's behind the scenes, as long as n's are quote unquote large. Here's some appendix. You can read this on your own Excel commands. Thank you very much.